Welcome to Learn Data Science with KNIME.
So what we're going to do here, we'll spend, I don't know, the next hour or so on this bit. Normally, what we would do in a breakout session like this is we would say, I'd be with you together in a room and you guys would be maybe in groups of 2 or 3 and you'd be working on the problem together and I would kind of float the room and you'd ask me questions. Normally I like to have people kind of beat the heads against the desk in a little bit of initial frustration, because that's how you learn, right? You learn by doing. But because we're all distanced, what I'm planning to do here is to actually build out the solution for you live so you can see me do it. And then hopefully you'll be able to follow along with me. If you have KNIME open in a separate window or something, you can actually just read, follow exactly what I'm doing, do it as I do it. And then if something's not working as you go or something, then you can ask questions and we can stop and make sure that everything's going to turn out okay. Does that sound all right to everybody? Okay, let's go ahead and get started. So we are in group 1. This is going to be the data access, blending, and prep group. So if you have this open, if you have the KNIME archive open, you're going to go, after you've imported it, down to Learnathon 2020. You'll go to Challenges, Group 1, and then click on the guy with the little KNIME triangle by it to open this up. And that's exactly what this should bring up. It should bring up the instructions with a bunch of these gray squares in the middle here. These are called meta nodes. You'll also have a folder here down below with the data. So up at the top left of my KNIME Explorer, I can see I have my data folder and my input, again, split into groups, because we're going to read this data in here in a second. So the first thing we'll start with here, again, the goal, right, is to predict departure delays. Before we even get within 100 miles of doing any sort of predictive analytics here, we actually have to make sure that we do our data cleaning, our feature engineering, getting rid of any outliers, doing our normalization. And the very last thing we'll do is split our data into training and test. And that's where this exercise for this group will stop. So that's what we're going to try to do over the course of the next hour. This is, I would say, probably the easiest of the 3 groups. So, if we have some beginners in here, that's good. So we're going to start with 2 different data sets. As I mentioned before, we have this airline data set that contains a bunch of airline-specific information. We'll see what's exactly in that data set here in a second. And then we also have weather information or meteorological information from a completely different source. So we want to start by reading those in. The way we can do that here, we're going to click on this data access here, this meta node, the gray box. You can double-click to open it, or you can go to right-click, meta node, and open. But I prefer just to double-click. It's faster. So when we do that, what we've done in each one of these meta nodes is given you some instructions about what needs to happen in the meta node. So the first we're going to do is read in this initial data set. So it says read the data airline dataset.table available in this folder data/1_input/group1. So here is that file in my KNIME Explorer, airline dataset.table. So I'm going to drag that into my canvas here, right in the middle of the square where the instructions are. And what it's done is it's created a table reader node for me. So a .table file is a particular extension within KNIME. It's our own kind of proprietary tabular data format. Now, if I want to double click on this node to configure it, there's not actually much that I need to configure. I'm just basically pointing it to the data set. It's just a path to the data set, which is pretty straightforward. So I can execute this data set, or I can execute this node rather, by right-clicking on the node, clicking execute. KNIME thinks for a second, and now it's read the data in. If I mouse over this black triangle, which we call an output port, I can see that I have about 621,000 rows and roughly, 30 columns. And if I want to see the data itself, I can right-click on the table reader. Now that it's executed, go down to read table, and let me blow this up so it's a little more readable. Here's what we actually have in this data set. So 621,000 rows, year, month, day, right? Our date, time information, things like departure time, arrival time, some identification numbers for the aircraft, like the flight number or the tail number, how much time they actually were delayed. We're going to use this later. The origin airport, the destination airport, so on and so forth. How long did they taxi on the runway? Did they get diverted? Was there a weather problem? So on and so forth. And we have this date stamp field here at the end. So we've read that data in. That's one of the sources we want. So let's go grab the other one. It says, let's read the GHCN daily source.xls file. So it's in the same folder over here in our data folder. Again, I can just grab this and drag it in. Now, since this is an Excel spreadsheet, KNIME knows because of the extension, well, I need a different node for this called the Excel reader node. Okay, that's all well and good. Let's double click on the Excel reader to look at its configuration. So when we do that, we see we have a few things going on here. So at the very top is we have the path to our file. That's already been populated for us because we dragged and dropped it in from the Learnathon folder. At the bottom here, we see we have a preview of our data set. So that looks pretty good with one exception. I can see that I have on my first row here what looks like my column names in my data set, and KNIME has instead, for some reason, assigned these generic column names of call 0, call 1, call 2, call 3. So there's an option up in here that I can change to actually fix this. If I go up to the column names here, I can click table contains column names in row number 1 by default, and you can see when I check that box, my preview has changed. It gives me a little warning message in red that says the preview is out of sync with the changes I've made to my settings. So I can click the refresh button, and what do you know? Now my column names have what look like to be appropriate. They've been appropriately populated. Whew, can't talk all of a sudden. And then along with that, I have guesses at what these different fields should be. For whatever reason, it looks like a lot of these are being assigned as string type, which is probably not correct, but I can always change that later if I need to. I'm not going to worry about that right now. These are the changes I can make here in the Excel reader. If I only wanted to read a subset of my data, column A through column G, rows 1 through 300, I could make that limitation here. But since I've fixed the column names, I'm going to say this is good enough for now and click OK. Then I'll click Execute and see what I've got. I've got 731 rows, 35 columns. And if I want to, I can actually go in just like I did before and look at the output table. So what do I have? This is meteorological data. I have the station name, the date stamp, some precipitation indicators like snow depth, weather. I don't know what snow is versus snow D. Snow depth, minimum maximum temperature, information about the wind, and then some other events. And then we have a lot of these red question marks on the right-hand side. What's going on there? That indicates a missing value in KNIME. So at some point, we're probably going to want to do something about all these weird fields over on the right-hand side of this metadata that seems to be populated with a lot of missing information. Okay, so we've read in our two data sets. And now what we need to do is we need to connect the output from the table reader to this output port of our meta node. Remember, we're inside a meta node here. So we actually want to send this data out of the meta node. And to do that, we just connect our ports to the appropriate spot. And now when we close this tab and go back out to the top level, you'll see that our little icon here is changed to a green check mark to indicate all of the nodes inside this meta node have been successfully executed and data is being passed out. And even at this part of the particular meta node, I could look at the individual ports to see what's going on. So I could, see my top port contains, this is my airline data. The bottom port contains my meteorological data. Okay, any questions about that, about reading the data in? I think that's pretty straightforward. Some of what we're going to do here in a little bit is more complicated. Yuki asks, how can I check the output? You can check the output of any node by right-clicking on it, assuming it has been executed. It must be executed first. You can right-click on it and then go down to the bottom and then pick. In this case, I have two choices because I have two output ports. So I happen to know my top one is my airlines and my bottom one is my metadata, right? That's how you would do it. Okay, let's go on to the next meta node here, which is feature engineering. So we're going to double click to open it, and we're going to have a new series of instructions. Again, I'm going to blow this up because I'm on a big screen and I want you guys to be able to read what I'm doing. Okay, so here's where we're going to start to make some changes to the format of our data and also filter out some things that aren't particularly useful. These are going to use some nodes that we haven't necessarily seen yet. So the first thing it says to do is let's convert the date columns in both data sets from the data type string to a native date and time format. And we can do that using the string to date and time node. So let's go to the node repository and let's look for string to. There it is. So I've got two versions here. I've got the string to date and time, then I've got one marked legacy. Legacy is the older version from past versions of KNIME. You don't want to use the legacy nodes, generally speaking, unless you're dealing with backwards compatibility. But since we're building a brand new workflow here, we're going to use the string to date and time node, the regular one. So we're just going to bring this in. And in fact, I'm going to bring it in twice because I need to convert the strings to date and times from both of my data sets. They both have timestamps. And I happen to know that the timestamps are not of the same format. So let's see how this works. If we open up the string to date and time configuration now, what this is going to say is, you see I have this green box and red box at the top. This is saying, well, which strings do you want to convert to date and time format? Well, I don't want to convert things like tail num or cancellation code. So what I'm going to do is I'm going to click the double arrow here to move all of these fields to the left exclude red box. And then I'm just going to pick the one I want, which happens to be called date. So now what this is saying is whatever conversion I'm doing is only happening on what's on the field that's specified in the green box. Now, what KNIME is going to do, I could have it try and guess what my format is here. You can see that there's this content of the first cell, 01-01-2007. So that looks like month, day, year to me. If I click on guess date and type format, then KNIME is saying, actually, it thinks that this is day, month, year. I actually don't think that that's correct because that's like the European way of doing it, right? So I'm actually going to make a change here and manually type this in. So if you ever need to know for this particular node what the different indicators are for hour, month, second, day, year, whatever it is, you can look in the description pane on the right-hand side to get some examples. It turns out that M, for example, is case sensitive. Capital M is month and lowercase m is minute. So you have to get it right. So I made that change because I think KNIME didn't get it quite right. Manually type that in. And we're saying we're going to convert this to a date. There's no timestamp involved. So we click on OK. And then click execute. And then it says, it gives me an error down here. I can see in my console, failed to parse date in row whatever. The text 13-01-2007 could not be parsed. So it turned out KNIME was actually correct in this case in the guess that it made. So the change that I made was wrong. So we're going to change it back to the way that it was. I'm going to rerun the node, click OK and execute. And now KNIME is happy with that. It didn't find any mistakes according to the date and time conversion that I provided. Now let's do it for our other file. So that was for the for the airline data. Let's do it for the metadata. So if we look at the metadata, again, we have all of these different strings. I only care about one of them. So I'm going to make sure that date is the only thing that's included in the green box here. You can see my contents of my first cell is slightly different than what I saw before. I don't have any hyphens in between, and the year seems to come first. So I'm going to let KNIME guess the date, type, and format by clicking the button, and it says, oh, no suitable format found. I guess KNIME has never seen this before. That's kind of a bummer. So what I'm going to do is type this in manually. 4 Ys for the year, MM for the months, and DD for the days. I'm going to specify this is only a date and not a date time. And let's see if that's going to work. And it did work. So the way that we can verify that this worked is after we've executed the node, we can actually go into the output table, just like we would any other time. And I can see that my date column here now has changed from what was a capital S to indicate a string. It's now a little calendar to indicate a date. And the reason that this is important is twofold. One, we want these two things from our metadata and our airline data to have a common format so that we can join them together later. That's important. But also having a native date time format is important so that you can do things like extract different date fields from your date. If you have a date and time format, for example, there's another node that I could use to pull out information from that date to say, oh, this was a Saturday, or oh, this was the month January or the month October, or there's all sorts of things you can do. You can calculate durations and other interesting things. Those things only work if you're in the native date time format, and so that's why this conversion from a string is important. Okay, let's keep going with some other stuff here. We're going to do this other stuff that's specified for feature engineering just on the top branch. We'll go ahead and connect this bottom branch because we're not going to do anything else with the metadata for the time being. We'll just go ahead and connect that out of the meta node. But we do have some other things we want to do up here. So the next thing it says is let's keep only records with the origin equals ORD, meaning we're only going to look at a subset of the data for flights that originated at Chicago O'Hare. And we can use the row filter node. Okay, so let's go find the row filter in our node repository. Bring this in up here and connect it together. So now we need to configure this. We're going to double click on the row filter and say, all right, I want to test the column origin. So I have to scroll up to find it. There it is. And then my pattern match is going to be ORD. And I'm going to include rows that match. So whenever I have something that matches ORD, I'm going to keep it. Otherwise, I'm getting rid of it for the field origin. So if I click OK and execute, I can see at a glance, I went from 621,000 rows down to about 31,000 rows. So I've definitely filtered out quite a lot. And if I look at the results here, I can double check and go over to my origin field, and I should see only ORD in that field, which is true. So good, I did that correctly. Question in the chat. For the second date, it said execute failed to parse date. Text 2007 cannot be parsed at index 0. So yeah, that means you've got something slightly wrong. Do you have the date format like this with the capital M's in it? That's the first thing that I would check. As suggested by AJ, you want to make sure that it's date and not date and time. Your locality is defaulting to US. That should be fine. The other thing is you want to make sure that you're only parsing the date and not some other stuff up here at the top. So double check and make sure that that's all set properly for you. You put dashes between the numbers. Yep, there's dashes in the top one, but not the bottom one here. So the metadata does not have the dashes. Yeah, and that's where looking at that content of the first cell, it's kind of hidden here, but that's where looking at that is important. Cool, good. I'm glad you got that squared away. Okay, so the next thing we wanted to do was remove these canceled flights. There's some flights in here that have a cancel code equal to 1. We want to get rid of those too. We can use the row filter again to do it. So we're just going to drag in a separate row filter node and connect it. Now removing the canceled flights will look a little different. So we will go to the column test, not the cancellation code, but rather canceled, which is an integer. We're going to pattern match where that equals 1. And instead of including, now we're going to exclude. So anywhere where we have cancellation equals 1, we want to drop those. So we click OK and execute. And how many rows did we lose? We just lost a few. We went from 31,800 roughly to 30,500. So not quite 1,000 rows, but it still did something. So that's good. Now we're going to encode our delay. I mentioned in the introduction, we have this departure delay field, or depth delay field that actually has the numeric value of whether something was delayed or not by how many minutes. And so we're going to turn that numerical value into a string that'll be delay or no delay. And the way we can do that is to use the rule engine node. So if we use the rule engine, you go pull this in from here. The rule engine has kind of its own specific syntax that I'll show you. So what we're going to say, we're going to look for this column dep delay. So if I scroll down the column list on the left-hand side, let's see if I can find it. There it is. What I'm going to do is build an expression in this bottom portion down here. You can see there's these 4 green lines. These are always included by default whenever you open up the rule engine node to remind you of what the syntax is. They're commented out with these characters here at the beginning. I could just delete these if I wanted to, but you'll always see them when you open it up. We want to build an expression that's going to have a syntax like this. And specifically, we want to say if the departure delay is greater than 15 minutes, we're going to call it delay. So this is how we can do that. I could actually type this in if I wanted to into the expression field, but I find that it's actually easier to build these by clicking around. So if I double click on dep delay from my column list, you'll see that it populates down in the expression. I have dep delay with these dollar signs around it. The dollar signs around it is just a syntactical thing to indicate that this is a column. Okay, so if dep delay is greater than 15, so now I could go up to my function and look for my greater than. I can click that and it'll insert a greater than. I probably would just type it in this case. And now I am going to type 15. So if my departure delay is greater than 15, then we're going to do something special. I'm going to enter this arrow character, which is basically an equal sign followed by a greater sign. So this is called my antecedent, everything on the left-hand side of the arrow. And now I'm going to enter my consequent. So my consequent is going to be, with quotes, delay. So this is basically an if-then statement, right? If my departure delay is greater than 15, set this field equal to delay. Okay. So what do I do in the opposite case? If it's not, if it's something other than what's indicated here by the greater than 15, well, then I can do a little bit of shorthand. I can say for everything else in the data set, I can type in all caps true, again, the little arrow, and then in quotes, no delay. So this is going to encompass everything in my data set. If my departure delay is greater than 15, assign it this value. If it's anything else, assign it that value. And we're going to append, by default, we append a new column called prediction, but our instructions said we want to create a new column called departure delay. So down here at the bottom, I'm going to type departure delay to distinguish it from the existing numerical field, which is called dep delay. So I know syntactically this is a little bit weird. The rule engine is kind of its own little beast, but hopefully it's not, once you've used it a few times, it's not too confusing. It's just unique in the way that you have to remember the syntax. But again, that's why we give you these green things here at the top to give you examples of the syntax. Okay, so we've assigned delay and no delay, created this new field. Let's see how it works. So I'm going to click OK here, execute the node, and look at the results. I should have this new field. New fields in KNIME that are appended always show up on the far right-hand side. It's called departure delay, and then I have these string values. So I've now done a binary encoding, basically, right, into this column. And this is the thing, if you do group 2 later on when you build a model, this is going to be the target field for the model that is built, this departure delay. Okay? So that's all we needed to do in part 1 of feature engineering. The last thing is we need to connect the results of the rule engine node to the output of our meta node. And now we're done with that first bit of feature engineering. Any questions about what I've shown you here? I know the rule engine syntax is strange. String to date and time, you can often get failures, but hopefully this isn't too bad. Again, if you have questions, feel free to unmute and speak up, or I have the chat open, I can see it. Can you send the rule engine syntax in the chat box? It's too small. Oh, my apologies for that. Yes. So this is the rule engine syntax. Yeah, sorry about that. I am on a pretty big screen today. Okay. Let's go on to feature engineering part 2. I think we're doing okay on time here. So let's open this up. Again, I'll blow it up. Okay. So first thing we want to do here now is join the weather data with the airline data using the date columns as the joining columns. So remember, we took our string dates before, we converted them to a common format, date and time, and we can now use that date and time to join these two data sets together. So to do that, we'll use the joiner node. And you can see that the joiner node has 2 different inputs. So we're going to take our airline data from the top, our met data from the bottom, and then let's configure this joiner. It says we're going to use an inner join and use the date columns as the joining columns. So when you open the joiner, you'll see your join mode up here at the top. You have the choice of, if you're familiar with SQL, you've seen these before. An inner join, which is most restrictive, left outer, right outer, or a full outer join, which is the least restrictive. So we'll do an inner join. And then we're going to add our matching criterion. We're going to join on our date. So you click the Add Matching Criterion button. Then you scroll down and find your dates. So here, it's almost all the way at the bottom. You'll find date with a lowercase d. And over here on this side, it's up at the top, date in all caps. So this is what we want to join on. There's some other options we could change here. If we went to the column selection tab, we could actually make some choices about, if we wanted to include some subset of the columns, we could make those choices here. But by default, the joiner is going to take all of the columns that are included in both data sets and always include them. So this is optional if you want to do some tweaking, but this is all we need to do for now, is just make sure that we're joining on the proper fields, which is date. So we'll click OK and execute. And we've got 30,547 rows and 65 columns. And if I look at the results of the join table now, here is all of my, let's pull it up, airline stuff on the left-hand side of my data set. Scroll over. Here's my metadata, right? So now we're all in the same table, joined on the date. Now, having said that, our data is still messy. And so there's some things that we can do to clean things up a little bit and make it more palatable, especially when we're going to be using this data to build a model with later. We definitely want to do that. So we want to handle missing values. There's several different missing values here and ways that we could attack that. So the first thing we want to do, let's remove the columns that contain more than 80% missing values. You can think about this, if I have a column in my data set that is mostly missing, when I'm going to be building a model later, if it's mostly missing, it doesn't have much predictive value. There's just not that much information in it. It's probably better for me to just get rid of this column entirely. And so what I could do is use the missing value column filter node. So there's a few different missing value nodes we're going to use here, but the missing value column filter node, this is the one we want to start with. Let's drag this in and connect it. When we double click on it, we're presented with all of our different fields in our join table. And I'll leave all of them in here as ones that we want to consider. At the bottom is where we set our missing value threshold. So this is set to 90% by default, but the instructions say, let's set it to 80. So we're going to set that threshold to 80. It's going to look through all of my different fields. And if any of them have missing value by percentage more than this, it's just going to get rid of it out of my data set. So we'll click OK and execute. Now I can see before, if I mouse over my output port, I had 65 columns. Now I've got 50. So I removed 15 columns using one node that were probably useless, right, for building any sort of predictive model. So that's a pretty good and easy kind of cleanup step that you can do. So let's dig in a little bit more, though, and do some additional tweaking on our missing values. So the third step here, it says if the data contains rows where the value of depth delay is missing, remove them. You can either use the row filter node or the missing value node for that. Let's use the row filter node for this part. So we've already used it in a previous context. So we're going to search for depth delay. This is the column to test. Not departure delay, that's the one that we just created, but depth delay. And then what we're going to do is, if you scroll down here, before we've been using this pattern matching, right, to search for something so that we could do a match. If we use the radio button, we can also look for missing values. And what we can do is, if we find any missing values, we can click on this radio button to exclude them. So this is something else you could do apart from just looking for particular things to match in the row filter node. You can also search for missings directly using the radio buttons. So when we click OK and execute, now this is a bit of a trick. It turns out that there actually aren't any missing values of depth delay, because before I had 30,547 rows. After I apply this, I still have the same amount of rows. So nothing changed. But you can see how, there are definitely cases where that would work, right? So let's do some other missing value removal. We do have a node called missing value, which does exactly what you think it might do. Handles those missing values. So let's bring that in and take a look here. So if we connect these two guys together and open the configuration, there's a few things we want to do. So the first thing our instructions say is to set the missing values in the string columns to a fixed value called unknown. So you see on this default tab, we have the different types of fields that are on our data set. We have strings we have integers, and we have dates, and these are organized right here. So for any strings that we run into that are missing, we're going to set that missing value, which is represented by a red question mark in the KNIME table. We're going to set that to fixed, and the fixed value will be unknown. I'm just typing that in right there. Now, our instructions say for integer columns, any missing values that we run into for integers, we're going to replace with the most frequent value in the column. So when I select this drop down for integers, I have several different strategies that I could apply here, right? I could look for, I could replace with the maximum value in the column, or I could, especially in time series, I can interpolate between the preceding value and the subsequent value and do an average, right? There's all sorts of stuff that I could do, but in this case, the instructions say pick the most frequent value. So that's what we're going to do. And then for the dates, if we have a missing date, we're going to remove those records. We're just going to get rid of them entirely. So if we run into a missing local date, we're going to remove the row. You'll see that this has an asterisk by it. And when we pick something with an asterisk in the missing value node, it gives us this little warning. It says, options marked with an asterisk will result in non-standard PMML. You don't need to worry about that for our purposes. It turns out that the missing value node generates a missing value model that you could then apply downstream. And one of the things it doesn't do well is remove rows. Generally, you don't want to remove rows anyway from your data set. That's not like a great thing to do. You want to find some other way of dealing with missing records. But we're showing you this here just because it is an option. And we want to show you not to be weirded out by the warning message that you're going to get as a result of using this. So don't worry about that. It's just something that it shows you. Now, I'm making these missing value interpolation options on a by type basis, right? So I'm saying for all my strings, do this. For all of my integers, do this. If I want to be more specific, I have my column settings here. I could go into my column settings and say, actually, for my departure time, I want to handle departure times by setting that to the previous value, whatever it is I want to do. The point is you can be specific about handling missings on a feature by feature basis, and that will override what happens on a by type basis. So it just gives you additional flexibility. I'm not going to do that here, but I just wanted you to be aware of it because it's really useful when you have to massage a larger data set with a lot of these different types of features. Okay, so we followed all of the instructions here exactly as we're supposed to. Click OK and hit execute. And we get this little yellow triangle. And what this is warning us of, and you see it in the console down here too, it says the current settings using missing value methods that can't be represented in PMML 4.2. That's okay. I don't care about that. It's just a warning. So if it was an actual error and things were really bad, then you would get a red X here and you would know, okay, I actually have to stop and fix it. But yellow triangle is just making you aware of something. Okay, so now we've interpolated or made changes to a bunch of these missing values. A couple other things we wanted to do here. We want to bin the flight distance into 3 bins. So each of our flights is traveling X number of miles, from Chicago to wherever, right? So we would like to bin those flights into 3 bins, short, medium, and long. And to do that, we can use what's called the numeric binner node. So let's look over here at the numeric binner, drag that into our workspace and connect it. And then to configure it, we're looking for the flight distance. So where is that? Flight number, it's just distance. Okay, so I click on distance. I want 3 bins, so I'm going to click the add button 3 times. 1, 2, 3. And what this is showing now is I just need to make changes. So we're saying that a short flight is anything less than 1,000 miles. A medium flight is between 1 and 2,000, and a long flight is greater than 2,000. So like maybe, I don't know what that would be from Chicago overseas, I guess. So to make these changes to the bins, I can click on bin 1, and I could say bin 1 is going to be from -infinity, sure, to 1,000, and I'm going to give it a name called short. So that's what I type in here. By default, it just says bin 1. I've changed that to short. and change this value to 1,000. Now I click on bin 2 up here. It's already set the lower limit for this at 1,000. So I'm going to change the max to 2,000 and call this medium. And then click on bin 3. And it's been set from 2,000 to anything greater than that. So I don't need to make any changes there, except to change the name bin 3 to long. And what it's going to be doing is overwriting the distance, which is currently an integer, with these 3 string values that I've just provided. If I wanted to create a completely new column and not override my column, I could click this checkbox and it would create a new one. But I'm actually just fine replacing the mileage with one of these 3 strings. So when I click OK and execute, that is what I will see is happening. If I go and look for my distance, here it is. It's now only going to be specified as short, medium, or long. So that turned out, yep, and good. I see different values. If I only saw shorts there, I would probably need to choose a different bin, right? But I actually do see shorts and mediums and occasional log in there. Yeah, like Chicago to Anchorage is a long flight. Okay, so we've done some binning. We've done interpolation of missing values. We've gotten rid of missing values. We've gotten rid of columns that mostly consisted of missing values. Here's something else that we could do as a quick filter. We could get rid of columns that contain only constant values. So just like having a field that consists of largely missing values doesn't contain a lot of information, a field that contains only a constant value, like a field with just the number 1 in it, for example, all the way through, that doesn't tell us anything either, right? If a field has no variability, then it's not good for use in a predictive model, so we'd want to get rid of those too. So to do that, we can use the constant value column filter node, which I can type constant into the node repository and go find. And then I can connect that here. So the options for the constant filter node, by default, it's just going to remove all of the constant value columns. Now, if you wanted to be a little more specific about how strings or numeric values are handled, then you could provide those here. But I'm just content with default options, which is, if it's a constant value, I don't care. I want it gone from my data set. And that's what this will do. So if I execute this guy, whereas before I had 50 columns, now I have 43. So there were 7 columns that were basically singular in the way that they were populated with information that aren't any good. So that node handles that for me there. And then the last thing here, as we've been doing with our other meta nodes, is we just need to take the results of this guy and connect it to the output port of our meta node. Any questions here about the second part for feature engineering? We haven't completely cleaned everything up yet. We have some more cleaning that we're going to do, but from a perspective of getting rid of missings and getting rid of columns that don't really contain information that we wouldn't want to use in a predictive model, that's what this portion of the meta node is for, or the workflow, I should say. Okay. So we'll back out. We're making good progress here. Let's move on to the outlier detection. This is optional, but we've got time, so I think we'll go ahead and do it. So let's click on this meta node and see the different ways that we could deal with outliers. So what is an outlier, right? An outlier is some observation in a particular field that is, kind of out of line or weirdly high or low relative to the other observations in that field, right? And there's different ways that you can calculate what constitutes an outlier, and there's different ways that KNIME can handle this for you. So let's start with the most complicated way. Let's say that we want to calculate this by we want to manually calculate and define what an outlier is, and then apply that. So we're going to start by looking at this first task here. Exclude all flights where the arrival delay is greater than the average of the arrival delay plus 10 times the standard deviation. Okay, so this is one way you can define an outlier. These are very, very extreme outliers. But let's see how we could do that. So the instructions say to use a combination of the math formula node and the rule-based row filter node. So let's start with the math formula. The math formula does what you probably think it does, which is takes some formula and applies it to your data set, does a calculation. So it says here we want to calculate the average of the arrival delay plus 10 times the standard deviation. Okay, so I just need to remember that. So if I was going to calculate that, if I pull in from the left-hand side here, my arrival delay, this is going to give me a row-by-row representation, which is not really what I want. I want to take the average over the entire over the entire column here. So instead of selecting the arrival delay here, what I really want is in the middle, this function, the column mean. So if I click column mean and then insert arrival delay in there like that, then that's what I want for the first part of this equation. So the average of the arrival delay plus 10 times, and again, I want the standard deviation of the entire feature. So here I can click on column underscore standard dev and insert the arrival delay again. So that's what I'm calculating here. This is going to be my cutoff for this, task number one. This is my cutoff for whether I think something is an outlier or not. So I've calculated this thing, and then let's append a new column, and we'll just call it cutoff. And that's going to do this calculation for us. So let me put this again in the chat in case you're following along. This is the expression that you can enter here to calculate what I'm calling the cutoff. So we're going to click OK and execute. And then, as you might expect, we scroll all the way over to the right, and we've got this new cutoff value. So what this is saying is, if our arrival delay is greater than 476 minutes, then this is an outlier, and we want to get rid of it. Like something's clearly wrong relative to the other observed delays that we see in our data set. And so now that we actually have this cutoff calculated, how can we actually filter those things out? This is where we use the rule-based row filter. So if we go in and we type rule-based into our node repository, there's the one we want. Rule-based row filter. Now we saw the rule engine before, and it has its own syntax, right? This is kind of similar. If we double click on this guy, we again have this expression that we need to enter here at the bottom. Basically what we're going to do is say if our arrival delay, so I can go down and double click on arrival delay to populate this. If it's greater than the cutoff that I just calculated, then we're going to call that a capital true. Here's the expression in the chat if you want it. So again, this is an if-then statement, antecedent consequent, right? If the arrival delay is greater than the cutoff, then I'm going to assign a binary value of true to this. Now, if I assign something true, what should I do? In this radio button at the bottom, I have the ability to exclude any true matches. So that's all that I do here. I have this one-liner, exclude the true matches. Click OK, and it's going to filter out anything now that has an outlier greater than whatever that was, 470 something. So now I've gone from 30,547 to 30,545. There are only two delays that fall outside of that rather expansive window. It's probably too generous, so we might want to narrow that down somewhat. There's a second task here to do a different calculation. I'm going to skip this for now because I want to show you the way that I would actually do this at KNIME. I probably would not do this manual calculation unless I had some really specific way that I wanted to calculate outliers. The reason why is, well, let me just show you this other way. So you could use what's called the numeric outliers node, which is going to be based on something called the interquartile range. But before I do that, let me actually show you what this looks like. If we saw violin plots earlier today in the demo that I did right at the very beginning, let's look at something called a box plot. I want to show you the box plot because this is useful to understand how the numeric outliers node works. So let's connect, we're going to use this box plot down here, connect to it. I'm going to say, let's look at just what we were looking at, arrival delay. So going to move all my fields over to the left-hand side except for the arrival delay. I'm going to generate a box plot based on that because the box plot will help me visualize what the distribution of the arrival delay looks like. So, and if I wanted to, plot multiples of these, and maybe we should, let's do security delay too. We can plot multiple fields at once in the box plot. All right, let's execute that. And then since this is a view, to see the view, the interactive view, we need to scroll down to the interactive view box plot node. And this is what's going to bring up for us a Chromium window with the box plot in it. So what is this showing me? If you're not familiar with box plots, this is a way of looking at a distribution of a particular variable. So what this is saying, and maybe you have seen these right back in Stat 201 in your undergraduate days. This middle line here, there's a box, there's a bold line in the middle of the box. That bold line is the median value. So for our arrival delay, the median value is 3 minutes. And then we have this box which represents the first quarter at the bottom of the box, the first quartile, I should say. The top of the box is the third quartile. So that's just looking at the distribution. So the first quartile has an arrival delay of -8 minutes, meaning the flight was 8 minutes early, not late. And then the third quartile is 28 minutes late. Beyond that, we have these whiskers. You can see the little dashed line and then a solid line here at the bottom. These are based on usually what's called 1.5 times the interquartile range. So the interquartile range is the distance between the first and third quartile. So the distance between -8 and 28. Take 1.5 times that value, and that's how you come up with the whiskers. Okay, anything beyond the whiskers, from a standard statistical perspective, would be considered an outlier. And so you see these O's and X's up here at the top, where some flights came in, 400 minutes late or whatever it was, super delayed, several hours. Well, there's a lot of these, but from a statistical perspective, these would be considered outliers. There's not as many of these as there are, what's happening in the middle of the distribution here. So what if we could come up with a way to basically strip out anything beyond 1.5 times this interquartile range and just not consider it? That's where we could use the numeric outliers node. The numeric outliers node is going to take this information that's used to build the box plot and use that to exclude information from our data set. So that's why I wanted to show you this first, because the numeric outliers node will do it without showing you the plot. But sometimes, usually, it's good to look at the plot so you can have a better understanding of exactly what's happening. And there's something else here. This was for arrival delay. Here's something else called the security delay, whatever that is, where you can see that this is a much smaller range, right? Its median is 0. It looks like the first and third quartiles are also 0, but then, so almost all of the time associated with all of these flights, the security delay is 0. But occasionally you get some that are not, and these are considered outliers. So just to show you that you can have much different variance from one feature compared to another. Okay, so now that we've looked at that box plot, let me show you. This is how I would think about excluding these types of observations in KNIME. I probably wouldn't go through the hoop jumping of calculating, the standard deviation and the average manually with a math formula. I would instead just use the numeric outliers node. So let's do that now. So here for the numeric outliers, we're going to bring in this node. And I'll just put it on a different branch because, the box plot is really just there so you can explore what's going on. In the numeric outliers, we can double click on this guy. Again, it says in our instructions, we're going to remove the flights in the security delay column. So we'll do everything here on the left-hand side except for security delay. We want to apply this only to security delay. And what this is saying is, we're going to calculate our outliers based on 1.5 times the interquartile range. That's the standard that was shown in the box plot. Now, if you want to change it, you can change it. You can make this IQR, 2.0 or 3 or 2.5, whatever you want. You can change that according to your domain knowledge and what you consider an outlier to actually be. But by default, it's going to be 1.5. And then when it finds something that it considers an outlier based on that box plot calculation method, what should it do? Is it going to apply to all the outliers, just the upper ones or just the lower ones? And then what should it do? Should it replace those outliers, or should it remove them? And if it does replace them, what should it replace them with? Should it mark them as missing or give it the closest permitted value? So say we'll remove flights with values in the security delay column that lie outside both the upper and lower whiskers. So yeah, we're going to apply to all outliers. We're going to not replace, but we're going to remove the outlier rows. And then we should be good to go. And so when we execute this guy, we have a few different ports here. We have the treated table, which is just going to be everything in our data set with those outliers removed. So how many did we get rid of here? 3545 down to 3540. We lost 6 rows, basically. So the security delay is not so wildly distributed that we actually needed to do a lot of treatment here. It just got rid of a few nodes. You also have some other outputs here. You have the summary output, which is going to show you, in fact, exactly how many outlier modes or how outlier rows were removed, which is nice if you just want to see, and then what the associated lower and upper bounds were. And then there's this model output port, which we won't go into for your outlier treatment. This is basically for applying outlier treatment to a training data set or a test data set. Okay. That is all that we wanted to do, I think, for this portion. So I'm going to take the top output port and connect it to the output of my meta node and then continue. Did anybody have any questions about this? I think I put in all the different expressions that were used so that you can follow along. Okay. Not seeing anything in the chat, so we'll keep moving. Okay, the final thing that we wanted to do, so we've done our feature engineering, removed missing values, we've done our string to date time conversions, we've gotten rid of our weird outliers that we know don't make sense. Now we're going to do some normalizing, and then the last step will be partitioning before we get ready to build the model. So for normalizing and partitioning, this says normalize the numeric columns using min-max normalization into the range 0 and 1. So it doesn't tell you what node to use here, but you probably could figure out that the node is the normalizer node. So we're going to start with that, connect our input data here, and configure it. So basically, for any numeric columns, and you'll see that everything that's included here is either of type integer or double. So these are all the numeric columns available in the data set. We're going to normalize these into the range between 0 and 1. So it just does that using standard normalization, where it calculates the mean and the standard deviation and applies to come up with the normalized values. Why do we care about that? Well, if we look at the input data coming in here, we have things like the taxi time, right? It has a particular type of range, but we have other delays in here as well. We have other numeric values. We have this meteorological data that it has a range between 100 and 1,000 or something, which is a different range than our taxi time on the tarmac. So when we normalize, what we're trying to do is make sure when we put everything into the bounds between 0 and 1, that's useful for model algorithms that are doing prediction, because otherwise they might tend to favor, when they're doing their predictions, features that have a wider variance. So we want to remove that bias, so to speak, from the data set by making sure that all of our normalization here is performed, and we're basically cramming down our numeric values to between 0 and 1. And when I look at the normalized results after I execute that node, oops, I didn't execute it, so there's nothing to look at. Let's try that again. Now you'll see that every numeric value in here has been compressed to between 0 and 1. So it's all on the same scale, so to speak, so that our models aren't going to accidentally weight something higher than it should be when trying to come up with its predictions. So that's an important thing to do. Normalization is really key, especially if you're dealing with numeric values that start with wildly different scales. So you'll notice here that we have this black triangle port output. This is just our normalized data. We also have this blue square port. This is the normalization model. we're not going to use that here, but you can imagine if we had a training set and a test set, that any normalization that we might apply on our training set, we would also want to apply on our test set. So if we had different branches here, maybe training on the top and test on the bottom, we could use a normalizer apply node to make sure that the same normalization strategy we apply to our training data is also uniformly applied to the test data too, so things don't get out of whack when it's time to see how our models are performing and actually do the predictions. So that's why we have those two separate nodes. But for here, we're just going to use the normalizer node. It's also worth pointing out that later on down the line, once you've normalized something, you've converted it into a space that's not necessarily very human interpretable anymore if it's just between 0 and 1. So you could use the denormalizer node to be able to convert those values back to their original scale, so that you could do visualizations with them and actually be able to talk about them in real terms. So that's what the denormalizer node is for. Again, not stuff that we're going to use in what we're doing here, but I just want you to be aware of those features and that they exist. So after we've normalized, the last thing that we're going to do here is this partitioning. This is the idea of where we split the data into a training set and test set. Usually our training data set is going to be much larger than our test and our validation sets would be. Now, because this data that we're looking at is time-based, right? We're looking at flights from January 2007 in Chicago, and they're occurring sequentially in time. The meteorological data that goes with it, obviously there's some autocorrelation going on there. Like, if today is sunny, then tomorrow is more likely to be sunny than it is to be, rainy or wet or whatever. So my point in saying all that is we want to maintain the time series, so to speak, for what's going on in this data set. So when we split the data into training and test, we're going to keep that date stamp in mind. Normally, if this was a classification problem where we were didn't care about the order of the data, then we would use a partitioning node to do this sort of split, like I showed you in some of the early examples. But here what we're actually going to do is use something called the date and time-based row filter node, because we want to keep that date time, as part of our data set. So let's use the date and time-based row filter node, connect it from our normalizer. We're going to make two branches here. So this will be our training set. And what the instructions say is that it's going to contain flights up to January 15th, 2007. So what I'm going to do is, in this configuration, I have the ability to select my start point and my end point. So if I want to go up to January 15th, 2007, I don't care about the start, so I'm going to uncheck this box. And I guess, too, it's worth pointing out, I would have to select the appropriate date and time column, but since there's only one, this is the only one I can pick. Then, since I've unchecked the start, what I want to define is the end. So January 15th, 2007, I could go in and, I could select it from, the little dialog by clicking through. That's all well and good. I probably wouldn't do it this way, select it through the calendar. I'd probably just type it in, right? Because you can go into the dialog and you can actually type it. It's a little bit faster. So this is going to be our end, and we want it to be up to that date. So we'll make it inclusive. If we uncheck this box, we would only get up to the 14th of January, but we want it to include the 15th. So I'm checking the inclusive checkbox, click OK and execute it. And now let's see, what do we have in the data set? We have, I need to find my date field. Here it is. That looks like January 1st, 07, all the way up through the 15th. So that's exactly what I want. Now, if I want to get my test set, that's going to be flights for the latter half of the month, right? So we got the first 2 weeks for the training. We're going to get the last 2 weeks for the testing. So we'll use a date and time-based row filter again. We'll mark this as our test set. And we're just going to do a slightly different configuration, right? Here, we don't care about the end. So I'm going to uncheck the end box. Instead, we care about the start. So here we want to start on the 16th of January, 2007, inclusive, and go to the end of the data set. So that's all that I typed in there. Hit execute that guy, and then double check, did we get it right? And there it is, starting on the 16th, all the way to the end of the month. So I have two roughly equal sized data sets, 14,000 rows against 15,000 rows that I could use to do my prediction. And if you start doing the group 2 exercise on your own time, this is basically where you'll begin. You'll be provided this data set already pre-processed for you and split into training and test data sets so that you can then start building models to predict that delay or no delay that we built in the rule engine node earlier. So that's getting almost to the end. But one thing, now that we actually have the training and test data sets written, they're all cleaned. We got rid of the missing values. We got rid of columns that aren't useful to us. We actually need to write these out somewhere, and that's the last bit here. We're going to use the table writer node to actually write these somewhere. So if I go to the node repository, I can use the table writer. You'll see the table writer node is red to indicate that this is a writer node. We've seen a bunch of these yellow nodes, which are transformation based, right? Now we're writing a data set somewhere, so it's going to be red to indicate that. And these nodes are really easy to use. You just need to provide a path. So maybe, I'm going to go in and browse, and what the instructions say is write it to this particular directory, data/2_output/datasets. So where you write this to is going to be different on your system than on mine, because on my system, I have in C users, Scott, I have a KNIME workspace that I'm using, this particular one. And then I have so once I found my workspace, and this will be different, yours is probably going to be KNIME-workspace. You can find the individual folder here. So this is going to be Learnathon 2020. And then what did it say? It said write it to data/2_output data sets. So we had to dig down to find it if we want to be explicit with what the instructions say. But really, you can write this anywhere so long as you know where you're writing to. And then give it a name, right? So I'm going to call this, RMDS training.table. And so when I execute this node, there's nothing really for me to look at or examine. You see there's no outputs here. That's because KNIME has written a file to my disk that contains all this information that I just created, right? And then something similar for the table writer. I could go through that browse bit again, but what I'm actually going to do is copy this path from my top table writer and copy it to the bottom table writer, and then just change the name, right? And execute it. And so now I have these two files. In fact, I can go see them probably. Let's go to the data folder, group 1. Oh, I have to go to output. Data sets. Yep, and there they are, RMDS training and testing. So I could create a new workflow, right? And just drag that in to a new table reader. There's the file that I'm going to start with when I go into group 2 and I start building my models. If you use group 2, if you start with group 2, you'll be provided with that data.
Thanks for watching. Hit the like button to let us know you've enjoyed this video and subscribe for more data science content. Visit grmds.org through the link in the description to access KNIME workflows and other valuable data science resources like online courses and webinars. Sign up is free.